the session. Greeting of the day. In today's class we are going to discuss about the solid state joining process of friction stir welding method. In earlier classes we have seen about the mechanical energy welding. It means the energy that we are giving, maybe the friction, maybe the force, maybe the explosive, maybe the diffusion, maybe the ultrasonic. All these things we have started and we have completed the friction welding methods. And in this class we are going to see about the friction stir welding. It is also one of the other method of friction welding, even though the heating occurs by the rubbing actions. It is another variant of friction welding. What is the necessary of this going of a friction stir welding? We want to know. We have come across the many arc welding methods and each have its own nature. When compared to SMAW, TIG welding, we have used the inert gases. Such like that here, the aluminium, importantly welding of aluminium is very difficult as it is melting at a low temperatures, very low temperature of a melting point having around 600. It is getting difficult to generate a heat and melt and solidify. In between, meanwhile, the microstructure changes also occurs. Therefore, we should not reach the melting point of the material. That is our agenda. Accordingly, we have formed this friction stir welding, which is a solid state joining process, which will not reach the melting point of the material, and therefore we can able to weld in the semi-solid or plasticized zone itself. Material heated and it will be a readily deformable condition. Readily deformable condition. At the time we are giving a pressuring actions or stirring actions and we are solidifying. So that is what. So basic problems with the fusion welding. Fusion welding of aluminium, like some grades of 2024, 7050, 7075 are, they have the ability to generate dendrite structures. We have seen this in the metallurgy in solidifications. Dendrite is nothing but a tree-like formation structures which is sharp, and the sharp incision points which generates a crack, which is not good for the material. That should be avoided. But what to do here? In the fusion welding of aluminium, the dendrite forms. It should not form. Then we should not do the fusion welding at high temperature. The temperature we should reduce. That is why we are going for the friction stir welding methods. Then it forms the porosities, and also therefore due to this dendrite structures, the mechanical properties, fatigue properties after welding reduces. We need more strength comparative to the base material, but here it is reducing, inferior. Loss of alloying elements. Some of the alloying elements which are added are evaporated due to its high temperature of the fusion welding process. So the nature of the element which are added for the improvement of the mechanical property we won't get. So what happens here? The loss of alloying elements also made in the fusion welding. Loss of strength. So inferiority of the mechanical, loss of strength in the heat affected zones. Solidification, liquid cracking. That is what? Dendrite causes the cracking natures. More reactive material, so reaction takes place. As aluminium belongs to reactive material category that we know. Therefore, some reaction takes place at high temperatures. When we are making the specimen to the increasing the temperature, the kinetic energy also increases, the reaction increases. So such things we should avoid. So this not happens in the fusion welding of aluminium. Therefore, we are trying to do the aluminium welding through a solid state. Solid joining of friction stir welding. So that is what our idea too. Therefore, how we can able to do this aluminium welding by the low heat input process, we can able to do friction stir welding. That is what now we are going to see. Maybe the electron beam welding also possible. Maybe the laser beam welding also possible. Now we are going to see this friction stir welding. It is invented by Welding Institute of UK in 1991, very recent. The recent invention this is. Most significant development in welding technology in the decade, it is a green technology. What is this green technology? The same word we have already seen for the friction welding also. No smoke, no filler, no shielding gases, nothing, no spark. So these things causes the environmental friendly green engineering, green environment, environmental free. It will not affect it. Therefore, we are calling this as a green technology. So, objective of the friction stir welding. What we have to do? We are generating the. What I am doing here in this method, I have taken the specimen of 2 specimens I have taken, and what I am going to do here is I want to weld in this zone. I am inserting a tool here, and I am going to stir. This action takes place. Stirring action I am going to do. So in such a way, the center part will stir. That generates stirring action, generates the heat. That he is going to make the plasticization zone readily deformable, and as it is, we are going to solidify. Generating heat at the workpiece. What is the use of? That is what the tool. Here, what we are using this tool. The use of this tool is to generate the heat of the workpiece, move the material to form the weld joint. For these 2 conditions, I am using the friction stir welding FSW tool. Friction and deformation affects the result of plasticization of the materials. Here there are 2 categories are there. One I am calling as an advancing side, one I am calling as a retarding side. What is this? When the tool is rotating in this direction, so it is rotating here. So I am calling this side as an advancing zone, advancing side, and here I am calling this as a retarding side. The clockwise which is rotating, I am calling that side as a advancing side. The other side I am calling this as a retrieving side. So here we came, the setup. You see, we want to weld 2 specimens of number 1 and number 2 are there. Here we want to do the welding methods. So how I can do? I have taken one tool. I have taken one tool components which contains a shoulder and a small pin is there. So what happens? This pin, I am going to plunge inside. I am going to plunge inside the 2 specimen. Here there is no gap, 0 gap. No, we have not taken no edge preparations. A flat 2 specimens I have taken. 2 flat specimens I have taken here. This point. I have taken the 2 flat specimens and I am inserting this tool inside here by plunging, putting a hole and going inside. After that, what I am doing, I am going to rotate with respect to the application of pressure and the rotation of this pin. Here the stirring will happen. See, that is what? Application of the welding pressure and stirring action on the friction stir welding tool. It is going to generate some stirring action in the middle. Therefore, what happens? This advancing side material will go to the retrieving side, and this retrieving side material come to this advancing side after stirring action. Therefore, we will get equiaxide minute grains, finer grains will get. Finer grains directly related to the high strength. So how we are doing? I want to keep moving in this direction. After rotating, stirring action, I am moving towards the other end. Here there is no, see, in this there is a line. There is no edge preparation we have done. See here, this line is a straight line. We have not done edge preparation. Edge preparation, it is a flat. Edge preparation is a flat. No V-groove we have taken. Just like that, we have placed the tool here and tool plunged inside. Tool plunged inside and stirring action takes place, and we are going to move those things. In such a way, we can able to weld this. The same video I have played here for our understanding. See, the 2 plates have been taken, a welding phase, we are keep on rotating, and it's from one side to the other side, it's moving with respect to pressure and the rotation of the tool. 2 parameters I have used. For the tool, I am giving pressure and also the rotating of the tool. See, after welding completed, I have taken out the tool and cleaned. Here we are getting the beautiful flat surface, but hole is there. This is to be cutted as a scrap. So this we can use. This total length we can use as a complete weld joint. no edge preparation, no filler, no shielding gas. Only we have used the tool to rotate. How speed it is rotating, how pressure is applied, with respect to that we can able to do the welding joints. See how we can able to go ahead. So a 2-second video will play you again here. How this various stages we are calculating to do those things. This is the setup of machine setup for making the friction stir welding process, and it have content it can be able to do in the simple CNC machine. We have a board and we have a setup and we can able to do this. See how the tool is used. This is called as a shoulder, and the shoulder, the pin is there which is going to go in depth up to the total thickness of the specimen. Not more than that. The pin profile should not be beyond the thickness of the specimen, as it is equal or slightly lesser than that of the, in case of a 10 mm plate, we can able to take 9.8, 9.7, like that we can able to take the pin profiles. See here in this setup we have the fixtures and we have fixed the tool over the above conditions, and now the plates we have to fix in between those fixtures and the stirring actions to be done. We have taken 2 plates here, and these 2 plates of aluminium AA1100 I have taken the grade material, and I am going to weld the small thickness, maybe 2 to 3 mm thickness of the specimen of aluminium I have taken. Low melting point. It should not melt at dendrite form. That should not happen. Therefore, I am preferring this solid state joining method. Through fixtures, I have fixed it. No distortion will take place. Due to this fixing actions, no distortion will take place. So first, plunging stage. I am inserting from where the welding has to be started. Stage 1, I am plunging inside the workpieces. After plunging inside, we have to move. When after heat generation, the small heat generation due to friction and plastic deformation will take place there. After that, this plastic deformation due to the rotation stage from the advancing side to the retrieving side, from the retrieving side to the advancing side, the material exchanges will happen. This rotating tool forces all to the around, all around. Therefore, we are getting equiaxide finer grain. See how? And then the welding phase occurs. Stirring of the material leads to welding. So, it is joining occurs in the semi-solid itself. We have not yet reached the melting point of the material. So, after completion, a smooth surface we will get. We have to know before about the tool geometry also. Tool has a shoulder whose rotating against the job generates most of the heat required. How this heat is generated? We know now we have taken on tool and rotating. But the idea of the tool to be more stronger than that of the aluminium. It means the workpiece. If it is lesser than that or equal to the what happens due to stirring actions, it will same melting point and same heating occurs. Then as like aluminium heating, the workpiece, the tool heating will also be there. So tool also will get wear, tool also will get damaged or plastically deformed position will achieved by the tool. If it is a tool itself plastically deformed stage, it will also melt. It will also mingle with the workpiece and welding won't occur further. Therefore, the tool should contain high wear, high melting point. The tool has a shoulder whose rotating against the job generates most of the heat required for the welding. So this is about the tool shoulder, this zone. Where is the workpiece here? I have kept the workpiece in this zone. I have kept the workpiece here. 2 workpieces I have kept. So this is a pin. The small L equal to thickness of the specimen. So this pin is going to go inside and plunge, and we are going to rotate. The pin on the tool, I am talking about the tool, shoulder and the pin. Pin on the tool is plunged into the job and helps stirring action. Metal in the solid state itself. Now welding, stirring, maybe not 1500, though not 600 we are reaching. Aluminum melting point 600 we are not reaching there. We are doing welding itself 400, 350 degree itself. So this research is going how to generate the heat with respect to various methods of pin profiles. So various pin profiles, maybe a cylindrical, maybe a threaded, maybe a conical, and conical threaded. Some different methodology creates the different forces. With respect to that, we can able to generate a heat in immediate, or otherwise makes the material finer. Due to these threading actions, aluminum material we can getting epoxy finer. Therefore, strength increasing can be done through these pin profiles. See, this is the diameter of the pin. We should keep understanding. This is shoulder diameter and pin diameter. Pin is going to go inside, shoulder is going to apply the force and hold the, it's like a drilling action first. If it is drilled, what happens here? The material which is inside, it right comes out, which is straight comes out. It should not come, we are doing welding. So it should be plunged back again, forced back again. Therefore, I am giving the shoulder diameter to stop the chipped material to come out. That is, we are stopping there and we are pressing back inside itself. And then the rotating, stirring and moves on. That is the use of the shoulder. So I have given a different methods of a straight cylindrical, maybe a tapered cylindrical, threaded cylindrical. See, threaded I have given here. So these are the variants of the pin profiles, which is going to generate a different heat and methodology with respect to increasing the mechanical properties. And maybe the square. This looks here, but it is at the bottom. It is a square. And then maybe a triangular. Each one gives a different effort, different heat. Accordingly, we can able to achieve the good mechanical properties. So here I want to play a small video clip here for your understanding. See how they are doing the welding. You can see there are two thickness plates are there. See, this is one thickness, another thickness are there, and we have a pin profile, a conical threaded pin. Now only we have seen this threaded pin, and now it is rotating. And see, the shoulder is blocking the drilled chiplets should not come out. That is why it is blocking there. See, the 22 seconds has been done. Within a minute, we will complete the welding process. Continues a fast welding. Automated system. The welder become operator, not a welder. For the manual welding, it is a welder. Here, it is an operator. So we will see how it is moving, and then further it moves. See how the weld surface looks very smooth surface. But with respect to these forces, we are getting a beautiful smooth surface of the weld joints. Two specimens we have taken, and with respect to shoulder and pin rotation, welding completed smooth. Now we understand the working, but even though we will see. For working, we have taken a 2.5 mm thickness, 2.5 mm thickness plate, and then 130 mm per minute speed. I am moving total length 130 mm per minute welding speed, and at the rate of rotating speed of a tool 600 rpm. In such cases, we can able to do. It is a common range. Stage 1, tool preparation. Stage 1, tool preparation I am doing first. Whether it is a circular pin, or cylindrical or threaded, that preparation we are doing. Preparation of the tool according to the thickness of the material. If the thickness increases, this pin profile also will have the effort. Second one, tool plunging action. We are going inside. A non-consumable pin rotating at 300 to 600 rpm. See, 300 to 600 rpm tool is plunged into the material. Therefore, heat generation and plasticized deformation occurs. Right. Now it is plasticization ready. Now we have to move and welding to be done. Step 3. It is a welding methods. What I am doing? Stirring of the material interfaces by tool and moving, leading to the welding actions. What happens here? The stirring tool develops frictional heating, therefore causing the material to plasticize and flow from the front of the tool to back up where it cools and solidifies. So when the tool rotates move forward, this tool sends the other material, plastic material backward direction. So it is tight rotating. Fine particles we will get. And as it is, when the tool is moved, this region will solidifies. Because heat is generated here and we keep on moving. This heat trying to make the material plastic. And we keep on moving. This plastic is already mixed with the material A and the material B. And as it is cooling down when the heat is moving forward. So after completion of the welding, plunge out. The tool is taken out. That is what step 4, plunging out material. So welding will be completed easily. What is the metallurgical factor here? The finer grains. We have already told you. The material cools with the finer grain structure than the parent material, because we are not allowing to solidify as it is, because we are keep on stirring. This stirring action makes a splitting of the grains, breaking of the grains. If the breaking action happen, it is equioxide. It's not developed by the metallurgical solidification. Technically we know this. So this equioxide finer grains we will achieve in this friction stir welding, friction stir welding methods. So that is what. So I would like to show you a small animation here. See how this happens in a simple method. If we have said in the original video we have seen spindles start to rotate and it slowly comes down and it has to plunge inside and it has to move. See, it has to coming down and it's plunging inside the total thickness. Small variation is there and then it moves, keep on moving, welding has been done. A simple method we can able to understand. So what are the process variables here? We know the process variables are tool rotating speed, tool have to rotate, then only heat can be generated. How much can be? Just approximately 180 to 600 rpm for aluminium. A thickness increases, speed reduces. What is this idea here? Thickness increases, speed reduces. Because you see, we are sending a small diameter thing. Diameter is equal to the thickness. Therefore, see, pin is equal to 1/3 of diameter of the cylindrical tool. This tool is very pinpoint. If you are rotating very fast at the hard point, the pin, there is a chance to break. It should not break. With respect to small pin, only the entire heating occurs. Therefore, we should carefully handle in terms of rotating. 600 rpm, it is a huge. We should handle for lower thicknesses. If the thicknesses increases, obviously this rpm also reduces. We can take with the large thickness we are hitting, it will break soon. Therefore, we should slowly rotate when it is possible. Then travel speed, how far? And maybe I am moving 13 centimeters per minute. 13 centimeters per minute we can able to move. So that automatic system approximately it is likewise it may differ. And the plunging depth, how much the pin profile is going inside, we know it is equal to thickness of the specimen, or otherwise it is slightly less than the thickness of the job. In the video also we have seen the specimen went directly to this location and it has moved the thickness of the specimen. Plunging force and also plunging force, it should be holded. Plunging this tool to be holded here, otherwise it comes out. After drilling it will be like a drilling action there. So it is to be tightened well and it should be rotated and then it should move. The shoulder should stop, the scrap chips item should not come out. Therefore we should give pressure there. That is what 330 to 70 megapascal at an approximately for aluminum we are giving. Tool geometry, we know this. Maybe a cylindrical with a profile pin, hard wear resistance. This we need hard wear resistance relatively material being welded. Which material we are going to be welded? It is aluminum. This is aluminum, so it's to be higher than that of that one. The tool which contain higher wear resistance than that of the specimen which you are going to weld. So pin 1/3 of the diameter of the cylindrical tool and the length of the slightly less than that of the thickness. This point we have discussed here. Okay. So this is what. So maybe this tool rotation may be the clockwise or maybe the counterclockwise, any direction. Whether I am rotating this direction moving forward or this direction I am moving forward, whatever it is, the idea. Tool rotation results in stirring and mixing. Higher the tool rotations generates the higher the temperature. The tool should rotate at high speed. Then it generates the high temperature. Then what we should do? Tool to be selected which having the highest temperature than that of the material that we are going to weld. If aluminum is going to weld, we should take steel or titanium, carbide, some hardened material to take. Then only it won't melt and it won't wear. If it is weared by skipping actions, what happens? It also will, pin will be wear out. Then where is the pin to rotate? Pin will not be there. Therefore, high wear resistance material to be selected as compared to the working welding material. So that is what high tool rotation causes the high temperature. We are taking an aluminum tool, aluminum material and high temperature, it won't happen. It will melt. It should not, it is to be taken care. Due to frictional heating results in intense mixing and stirring. Yes. Travel speed. Now only we have seen this. Effect in flow of stirring material from the front to the back. How fast it is moving. Accordingly the stirring, accordingly the mixing also will happen there. So shallow plunge depth and deep plunge depth, which one we need? Shallow plunge depth does not touch the contact workpiece surface and thus cannot move the material. But here, in this deep plunging method, shoulder plunge into the workpiece produces the excessive flashes, producing the significantly concave weld and leading the local thinning of the plates. So this is to be taken care. So one more is there, plunging force around we know 30 to 70 megapascals. So this we have already seen the various pin profiles. One important thing we have to consider. So that is microstructural classification, how this is formed. I am telling the A part is unaffected zone because this is the microstructure of the cross section I have taken. After welding I have cutted, I am seeing here how it happens. I have welded here, this is the zone, see. Let us consider I have welded in this setup. So here this is the shoulder and I have welded here. Here I have welded. So this is the setup, please carefully understand. So shoulder I have kept and this is the workpiece. So I can tell like this. So this is the workpiece. Here or there. So workpiece it will be. So here I have a pin tool. Here I have the tool. So the rotating point is D. D is going to receive more heat. So D is the weld nugget. And then the nearby zone, nearer to the D I have C. C belongs to thermomechanically affected zone. Thermomechanically affected zone. Then A, it is heat affected. It is not, mixing is not happen here. But when the pin profile is stirring action takes place, here the metal itself mixing. But the B point, only heat is distributed from the pin to the workpiece. So it be, both sides will be heat affected zone and the other two ends are unaffected zones. So the advantages, so no filler, no flux, no shielding gas. Therefore we are having the fixtures, therefore no distortions, no smoke. It is called as environmental engineering, green technology, narrow heat affected zones, finer grains and recrystallization microstructures. We are getting hard work conditions with no entrapment of oxides. In the fusion welding process, this oxides also takes place, but it is not here. Gas, we are not using CO2 gases. Low power consumption, so dissimilar material we can able to. One side we can take aluminum, one side we can take able to, another take steel, some other we can able to do. But it having more limitations also. It having a richer clamping fixtures are needed, as we have seen in the video. And visible end hole at the last we have seen, one end hole is there. One small end hole comes, that is to be taken care. It should be cut as a scrap items. If needed, inability to make the filler welds we are not doing, only as it is tool is rotated and it's welded. Alignment critical, straightening needed. Initial cost is high and low welding speed. I am comparing here two methods, one of a fusion welding process, it means a solid state joining and fusion welding. I am comparing here, this is two. with respect to various parameters. Microstructure here in the friction stir welding, I am getting the finer reconciliation materials. It means due to this rotation we are getting breaking this development of the grains. Finer grains we are getting. So here the cast dendrite, a dangerous one. And then appearance very smooth in the video also we have seen. In here it is very rough. Distortions, we are using fixtures, so it is negligible. It is highly significant. Consumables we are not using, no gas, fillers, flux, nothing we are using here. Very good. It's green. Here it is fission welding, gases, fluxes, fillers, everything is required there. So mechanical property it is superior because of finer grains. There it is a normal. And then the fatigue life it is excellent. Here it is again it is normal. And corrosion behaviors it is here also excellent. Oxidation not happens. There it is a normal. And then the impact on the environment with respect to environment no smoke. It is negligible. So it is very significantly smokes are and sparks or flashes or radiations are coming there in the all fission welding process. Running cost is less and there are many fillers and equipments, consumables positive are higher there. In here the running cost means we have only tool we have to prepare, but that is also we have to consider. So joint configurations you see, I'm using some butt joints here, we can able to do weld here. So to here in this L preparation I can able to do connect and then you can able to stirring action you can do. Likewise also stirring you can do. Here also 2 plates I have taken and I am going for the depth pin went inside and I can able to do here. It means all I am doing in the down hand positions, 1G positions I am doing, that you have to note. So here triple plate I am keeping again. Here I am again simply T joint. Here also again slightly cross run I am doing. So such possibilities are there. So what are the applications where we are using? In the aerospace, wings, fuselages, cryogenic fuel tanks, aviation fuel tanks, aircraft structures, excellent external aircraft throwaway tanks. Where are the parts of aluminium we are using? Though this application comes in aerospace to reduce the strength and we have to fly there. We should not take heavy steel materials and we can't go. So there we are using the aluminium, and there if the aluminium used, this fission welding properties will change. Therefore dendrite will come. That should not come. Again we are going for the solid state joining process. This obviously connected with the aerospace applications. In marines and deck fans, bullheads, floors, hull and superstructures, refrigerating plants and so many. Here also in the automotive constructions, automotive case handles, wheels, tailored blanks, armor plant vehicles, motorcycles, bicycle frames we are using. We are getting strength. And then fuel tankers, suspension parts, everything with related to automotive. And related to constructions we see reactors of powers, chemical industries, pipelines, heat exchangers, air conditioners, offshore drilling rings. So in the railways, high-speed trains, with carrying the more weight, we cannot be able to move fast as like aeroplane. So we are reducing it through aluminium, and it becomes a high-speed train. And obviously fusion should not do, and obviously we are doing for the solid state joining. So container bodies, railway tankers, wagons, and underground rolling stock. So many applications are there. So the summary. In welding, we have seen today about the solid state welding process. In this we have seen about the friction stir welding. So with respect to these advantages, applications we have seen. The remaining part of the subject we'll see you in the next session. Thank you. So here I would like to play a small video clip for you. You can able to see this.